In this part of the lecture, I'm going to show you some empirical evidence from a couple of freeway networks that I've studied many years ago during my PhD, as I was interested to see how the MFD or NFD of freeway networks look like. So I looked at some loop detector data from Chicago, Portland, and Irvine, and I started plotting them for different days and compared them against each other, trying to characterize them. So I can't remember. I think this is either Portland or Chicago. Sorry, I can't remember which city this was relating to among the three cities that I looked at. But these are some empirical MFDs, and you can see that for on different days, and you can see that obviously I have average network occupancy because loop detectors do not give us direct measurement of density. They give us occupancy. But I could get flows from the loop detector. So for example, in Chicago, I had maybe about 100 loop detectors across the entire freeway network. And I just did I took the weighted average flow and the weighted average occupancy to plot these MFDs. And you can see that, yes, we have kind of an uncongested branch in the MFD, and it goes high, 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 and then suddenly we move to the congested branch. So far it's very well defined, right? But then we start seeing a hysteresis. So this is called the hysteresis. You see this branch that so when the density is going down, so far density is going high, density is going high, density is going high, up to this maximum occupancy or density of like 20%, maximum occupancy of 20%, right? But then when the occupancy is going down, maybe in the afternoon, when the network is getting less crowded, instead of coming back on the same path that it went up, instead of going this way, we can see that in the MFD that a hysteresis is formed and density goes down, but with various smaller flows. So look at this point, for example. So this point on the MFD, at this time of the day, for the same density of, I don't know, something between 10 to 15, let's say 12% occupancy, it gives us the flow around maybe a little bit less than 1,000, while at another time of the day, for the same network occupancy, we observed almost 1,400 vehicle per hour. So there is a big difference here, right? There is a big loss of flow. And that comes from the fact that traffic was not distributing. So in this hysteresis side of the MFD, when we see something like this, the main reason is the heterogeneous distribution of traffic. So traffic is not homogeneously distributed. As a result, the average flow goes down. Why the average flow goes down when we have inhomogeneous traffic? Imagine this link has a flow of 0, and this link has a flow of 2,000. So what's the average? The average is 1,000, right? So of course it goes down. So when the traffic is inhomogeneously distributed, for example, in this extreme case, 2,000 and 0, the average is somewhere in between. So it's the same thing here. When the average, we'll see a loss of average flow here because traffic is very heterogeneously distributed. And another interesting observation that I had was from different days. So this is April 22, this is April 25 to April 27 in 2011. And we could see that the maximum flow that we could achieve at the network level is not fixed. Remember, we had this brief discussion before that capacity is a tricky measurement to work with because capacity is also not fixed at the link level. Link capacity is not fixed. It can change even during a day. It can change day to day. Same thing happens here in the at the network level when we look at MFD. The maximum average network flow is actually varying from day to day. And interestingly, the size of the hysteresis, for example, on April 25th and April 27th, we either there is no hysteresis or the hysteresis is very small. You can see the hysteresis are very small compared to April 22, which we saw a very large hysteresis. So for some reason, it might be because of the rainy weather, it might be because of a few accidents across the entire freeway network. We see this heterogeneous traffic compared to other days. And again, if you want to now zoom in a little bit more into this hysteresis phenomena, which is usually following a clockwise hysteresis, we call it. And if you try to break it down into different times of the day to see so this hysteresis here, from what time of the day this is actually coming from. So look, the black dots here is from 0 to 1 p.m., from 1 p.m. to 5 p.m., and then from 5 p.m. to 9 p.m. So this is in the morning, things are getting congested, it goes high, it's generally it's going, apparently it's going with very homogeneously distributed congestion. Then in the afternoon, things becomes much more congested. So this red part, these red dots represent the afternoon peak period at that in this specific network. So until 5 p.m., things are becoming very, very congested. And then from 5 p.m. to 9 p.m., when things are recovering in the network, it comes down this way. So not only we can relate the hysteresis to that inhomogeneous distribution of traffic, but we can also relate it to the loading and unloading of the network. So in the morning, in the PM peak, when the network is loading with a lot of vehicles, things are very homogeneous. Things seems to be very homogeneous, at least relatively homogeneous. But in the evening, in the early evening, when the network starts recovering entirely, it's when the network is becoming empty over time as we're getting closer to midnight, things seems to be very inhomogeneously distributed. Traffic seems to be very inhomogeneously distributed here. And that's why this hysteresis happens. And again, this suggested a very interesting phenomena in network traffic, that recovery is inherently heterogeneous. The network traffic, when it is recovering, is inherently very heterogeneous compared to the loading or when it's becoming congested. And again, a very similar phenomena was previously also observed at the link level, where when a queue is forming on a link, usually it forms very gradually and homogeneously. But when the queue is actually dissipating at the link level, we call it fragmented queues may form. So the whole queue may fragment into multiple smaller queues, and then it becomes very heterogeneous. So similar phenomena seems to be happening at the network level, which is causing this loading versus unloading pattern, and as a result, the hysteresis that we see in the MFD. So here are some more empirical evidence from some other networks, different days. You can see here I distinguished between the morning and afternoon. You can see that sometimes in the morning it's no hysteresis or very small hysteresis. Afternoon has a very large hysteresis, or it doesn't have to be the same. I mean, some days it's the other way around. This is morning, this is afternoon, morning, afternoon, morning, afternoon, and morning and afternoon here. And every time you can see that the size of the hysteresis may be different. The maximum flow that we can achieve at the network level in each day even differs from the morning to the afternoon. So very interesting phenomena. Next, I'm going to talk about a very simple model based on this concept of MFD and related to the conservation of vehicles at the network level. So remember the LWR model, which was also based on the conservation of vehicles, which we said the change in the density over time is equal to the change in flow over space, right? A similar thing can be described and formulated at the network level based on MFD. So the changes in the number of vehicles in the network can be formulated as the number of vehicles that are getting into the network minus the number of vehicles that are going out of the network. So this is the inflow, this is the outflow, right? So this is a simple conservation law. So input flow is coming from the demand, right? So how many vehicles are actually starting their trip. But the exit flow or the outflow can be described by the MFD. So imagine this MFD. So this is an MFD interpretation or representation, which on the x-axis, I have the number of vehicles in the network. And on the y-axis, I have something we call it network production or a trip completion rate. How many trip completion rate? How many vehicles can finish their trips in a unit of time? It doesn't have to be hour. It could be any time. For example, every 5 minutes. How many vehicles finish their trips or reach their destination every 5 minutes? And on the x-axis, I have this vehicles in the network. We also call this network accumulation. Network accumulation. So this is equivalent to the MFD because look, previously we said MFD is the average network density versus average network flow, right? So what is density here? I mean, look, in this, here I have network accumulation, number of vehicles in the network. So if I multiply this K by the length of the network, L, what does it give me? It gives me the number of vehicles in the network, right? Because K, capital density at the network level, can also be described as the total number of vehicles in the network divided by the length of the network at any time, right? So if I multiply this K by L and also Q by L here, so this gives me the total number of vehicles in the network. And on the y-axis, I have what? I have, it used to be flow, which is vehicles per time, and now it's multiplied by some kind of a distance. This is also called, I think this is also called network production. It is equivalent to this relationship that we're seeing on this graph, which says, as the number of vehicles in the network starts increasing, sure, people are more and more finishing their trips, right? But then at some point in a range, when the number of vehicles in the network is large, in between a range, things are becoming a little bit congested, and we no longer see an increase in the trip completion rate. Rather, the trip completion rate reaches a maximum point, very similar to maximum flow or capacity. So people can only, the network production is limited to this maximum point here. And then as the number of vehicles in the networks keeps increasing, things are becoming very, very congested, and people are not reaching their destination as fast as before. So this network production actually goes down. Which suggests the network is fully congested, or not fully, but I mean very heavily congested. And because of the congestion, people are not reaching their destination. So this G, or network production or trip completion rate, keeps going down. So this whole function, which is equivalent to MFD, in the literature, it is also called something like exit function. Okay, it is also called exit function. And if we have this curve, capital GN, this can give us this outflow. So given any number of vehicles in the network, you tell me what's the number of vehicles in the network, I can estimate how many vehicles exit the network or reach their destination per unit of time. So that will give us this exit function. So again, very similar to the LWR model, we are saying, or basically the conservation of vehicles at the network level. The changes in the number of vehicles in the network is equal to the input flow, which comes from the demand, minus the exit function. And this is only for one reservoir system. So imagine we're modeling city as one entire system, one entire block. We can extend that to two reservoir systems or multi-reservoir system. Then this differential equations that we wrote here needs to be expanded. So then we can actually write four differential equations. So which one of them says, what is the change in the number of vehicles going from zone 1 to zone 2? So imagine this is zone 1, this is zone 2. So dn11 over dt says the change in the number of vehicles going from 1 to 2. dn21 over dt represents the number of vehicles, the change in the number of vehicles that go from 2 to 1. We also have, sorry, N11 is not that one. So 1 to 2 is this one, and 2 to 1. So 1 to 2, 2 to 1. And we also have some vehicles starting their trips at the same zone and ending at the same zone, right? So we can also have the change in the number of vehicles that are going from zone 1 to zone 1, and also the number of vehicles that are changing from zone 2 to zone 2. And then look, this is basically the same. It's the inflow minus outflow. Inflow minus outflow. Inflow minus outflow. Inflow minus outflow. And this M here is that exit function that we were talking about. And again, don't worry about this multi-reservoir traffic model. I mean, it's a little bit more advanced here, but I just wanted to introduce it to you because I just want to highlight that we can model the entire city as multi-zones and multi-reservoirs and have a very simple model based on some differential equations to actually describe how traffic behaves, how things gets congested or propagated and dissipated across the entire network. Again, this is very similar, as I said, to LWR model at the link level, because imagine you compare LWR model versus a car following model that you do in AIMSUN. So when you do car following model, it takes a long time to run, right? It takes a few minutes to run depending on the size of the network you're simulating, because it's very computationally expensive. You have to model each individual vehicle. They all move at every fraction of a second. You have to calculate the speed, acceleration, etc. So it's very heavy in terms of computation. And that's a microscopic example. But in a macroscopic way, things are more aggregate. We can run it very quickly. There's no simulation. Everything can be done analytically with simple math. So it's just solving these differential equations that can be happening in a fraction of a second rather than waiting a couple of minutes to run a microscopic simulation. So with a few differential equations, we can actually see how traffic evolves over an entire network. I want to show you the paper because that's one of the key references in MFD. It's for the first time in the literature back in 2008, they used some data from Japan to show that MFD exists and can be derived, can be estimated from some empirical data. So if I show you the data here, the actual paper here, you can see that it's very similar to all the topics that we talked about here. So it's called Existence of the Urban Scale MFD, Macroscopic Fundamental Diagram, some experimental findings. So they talk about the data on the site. Look, they're taking the average, the weighted average of occupancies, weighted average of flow, very similar to what we've just talked about today. And then look on the left side here, on the left top side, you see data from individual loop detectors, but then when you average them, you actually see a very well-defined low scatter MFD. You can look at the network level density versus flow. You can look at the network level density versus speed. You can also look at the network level speed versus flow relationships. So this is coming from the weighted average flow and unweighted average occupancy. And then they're plotting some time series to discuss that. And then they conclude that MFD actually exists in reality. So this is the area that they're calculating. So this is part of Yokohama, Japan. They're using GPS data from taxis. Very similar. Remember in the first assignment, you worked with some GPS data. So you could actually use that data to actually do some MFD calculation if you want as well. So they use some GPS data from Yokohama for this specific area that they have shown here, and they wanted to estimate the MFD for this specific area. And again, look, the estimation of density is a bit more complicated. Number of vehicles in the network is density multiplied by the length of the network, very similar to the thing that I just touched on in my slides. And then this is the MFDs that they plotted and have shown for that specific city, which the number of vehicles in the network versus the speed, the average speed in the network. So again, very similar to the speed density relationship at the link level, but this is now at the network level. So instead an x-axis, instead of being density, it could be just the number of vehicles. So look, one of the interesting application of this is that imagine you are managing your traffic in the city, and you want to make sure the speed doesn't go below 20 kilometers per hour. So that means you have to somehow keep the number of vehicles in your city below 4,000 vehicles. If the number of vehicles in the city exceeds 4,000, if it goes to 8,000, the average speed in the city will go down to 10. And even if it goes to more than 12,000, it will even get more congested. So this MFD is later used as a mechanism for traffic control. Which again, it's a little bit beyond what we're going to cover in this course, but just wanted to give you an example of how this MFD is used in reality. They use it for traffic control. They want to keep, for example, if you want to keep the average speed in your city around 20, that means you must somehow keep the number of vehicles in the network below 4,000, either by encouraging them to shift from driving to public transport, or shift their departure time, or by perimeter control, we call it. For example, you don't, just like ramp metering, instead of letting everyone into the city, how about we gradually let people into the city, breaking them down, spread the peak. So that would help with managing the total number of vehicles that are in the city. So have a look at this paper. It's a very interesting. It's not super difficult to follow. It doesn't have complicated math. Very empirical paper from 2008. So have a look, and it will give you a lot more insights on MFD calculations and some of its use.